Okay, differential equations, lesson 6.2, day 2, the method of Frobenius. You can see that is our learning target. And what exactly is happening is we're picking back up from where we were last week. We're now going to say that we have a regular singular point of a second order differential equation. So let's just say we have a regular singular point. And what we're going to see is then there exists at least one series solution of this form. Now, of course, as you're looking at that, you might think, well, this doesn't seem to be any different. You glance at this, you'd say, hey, no difference between what we were doing so many other days. But you begin to look a little more carefully. You're going to say, no, wait a minute, there is a difference. There's a big difference. Look at that exponent. All of a sudden, it's not x minus x naught where we're centered. Let's center ourselves at a regular singular point. All of a sudden, it's not just an exponent of n. Now it's n plus r. And r is a constant. Or, as we're going to see, even in our example in just a minute, maybe constants plural. Maybe you'll wind up with a couple of possibilities for r. What I've highlighted in green on this far right edge is also very important. If we do have that r there, you can think, oh my goodness, if only we could go back to the form where we just had x minus x naught raised to an n. You could. Remember, r is a constant, and we could just factor that out, pull it completely out of sigma. And in that regard, then we're right back to where we started. So tell you what, we're going to make some basic assumptions here. We have y is equal to n equals 0 up to infinity. Let's go ahead and say y prime would be c sub n. And as we continue this on, we're going to say bring down your n plus r. And then you'll have x minus x naught to this n plus r minus 1. But maybe here is the surprise. When I plug in n equals 0, do I necessarily have a constant? No. So when I take a derivative, does a term disappear? No. So do I start from n equals 1? No, I'm going to keep it at n equals 0. Right? Because, look, as you were to generate this, you could say, hey, I'm going to start writing out my original form. C sub 0, x minus 0, and this is up to the r power, whatever that r may be. It's so abstract. Plug in a 1, and we'd have, here's your c sub 1, and we'd have x minus x naught, and now we've got our 1 plus r, and you get the idea. You start taking derivatives, you have no guarantee that you're taking a derivative of a constant. So our counter doesn't change, unlike what we were seeing earlier. So that's the first tremendous big difference that we're seeing. Likewise, we could take a second derivative, and once again, the same thing is at play. We can say, look, yes, we can bring down another power. Here's your n plus r minus 1, and we'll have a x minus x naught, and here's a n plus r and a minus 2. But once again, we have no guarantee that we have lost a term by taking a derivative. And because we don't have that, we cannot truncate or drop off a term. So, wow, look at the world of difference that we have here. So tell you what, we're going to take these forms that we have here and we're going to just plug them in. We'll say, look, in the original differential equation, we'll have 3x, but we're going to multiply that to this second derivative, which has gone from n equals 0 to infinity, and here's our c sub n, and here's our n plus r, and n plus r minus 1, and we'll have our x minus x naught to an n plus r minus 2. And then we'll say plus y prime. Well, that might be a much easier substitution to plug in. We'll have a c sub n. Here's an n plus r, x minus x naught. Up here we have an n plus r minus 1. And then finally we'll say minus what we have for our original y. We've got from n equals 0 to infinity of c sub n, x minus x naught. Up here is our n plus r, and that's all equal to 0. And we just have to deal with this pesky r, but let's also state the obvious. As a time saver, if you would like to immediately do some distributing ahead of time, you may. What I'm getting at is that first summation, I hope you can see that, yes, we're going to go ahead and distribute a 3 in, but we're also going to multiply an x in as well. And when you add in an x power of 1, remember we always will use that exponent property. We're going to add one more power of x to this mix here. So just add a 1 to that n plus r minus 2. You can quickly see that will become n plus r minus 1 now. And then, of course, we're going to have our second term, second sigma unchanged, and our final sigma, our third sigma, unchanged as well. So we're getting there slowly but surely. Now, what I do want to immediately point out to you is, if a student were to just glance at the notes right now without having heard anything that we were just talking about, undoubtedly what kids are going to immediately have catch their eye will be these R's. Because, assuming that you've gotten some good practice earlier, going through these solutions, you'll probably say, hey, I had the general idea before, but now you've got all these R's. And tell you what we can do. We could say, hey, I'm going to factor out an x to the r. I'm going to just pull that out. And then happily, nicely, you're going to have at least a little bit simpler of an expression. We'll have an x minus x naught just to an n minus 1. And at least with the powers of x, at least that part of the problem will look just a little bit more familiar. Of course, there still is going to be that strange issue about the r's being elsewhere. They're still going to be present, as you just have your first sigma and your second sigma. But right here you can think, well, my goodness, at least it's a little bit better. Well, at this point, because my powers of x minus x naught look a little bit different, and by the way, forgive me, what is our singular point here? Let's go back and review just for a minute. We should have done this earlier because this would have made the problem so much easier to write out at least. It's going to be 0. We talked about it's when that lead coefficient function could equal 0, right? We could say if we set 3x equal to 0, we'd get x is equal to 0. So, as we do that, and if we were to just bring this up here, if we said divide everything by a 3x, you could see that, sure enough, that power of x down below, x being 0, it only shows up once in that first fraction's denominator, and it only shows up once in the second. So we could say that x equals 0 is a regular singular point. Now, everything that I've written out so far is in fact fine. It's not incorrect whatsoever. But our x naughts right here are really 0. So I'm going to say let's let x naught equal 0. That was the problem point. That's the point where we'd say, oh, hey, if we were to make a series around that, we'd be in trouble. So tell you what, I'm actually just going to erase this. You could just exit out if you'd like. And it's going to be a slight change as you look at that. But it's a significant change, as you look this through. By the way, if the singular point would have been a 1, we would have had x minus 1s here and so forth. But it's at this point where we could say, oh, I wish all the powers of x, or x minus wherever that singular point were, had the same power. So I'm going to say let's let k equal n minus 1 here. I'm going to let k equal n minus 1 over here. And I'm going to let k just equal an n over here. Because ultimately what I'd like to see happen is I'd like to see all powers of x inside of sigma have the same power, preferably something with a nice simple k. And as we go through that, God bless you, we'll have this x to the r. And think about this. If n is equal to 0, your k here, now this can look weird, is negative 1. Wow. Look at that. That can get a little uncomfortable at first. And then you could say, well, let's see, n then would equal k plus 1. So I'll have 3 c sub k plus 1. This n right here, again, would be k plus 1. So I'll have k plus 1 plus r. Same thing, with our power. Here you just have n plus r. No, I'm sorry, the n, of course, is k plus 1. But if you have k plus 1, the 1 and the minus 1 are going to cancel out. You'll just have a k plus r here. And then this will be x to the k. So we're just going to go through this step by step and change things up a little bit. You come over here, if n was equal to 0, here we go again. This means that k would equal, surprisingly, that negative 1. And that means n here would be k plus 1, so we'd have a c sub k plus 1. This thing right here would be, n is k plus 1, so we'd get k plus 1 plus r. And this would be x to the k. And then finally, as we come over this way, you could see we've got n equals, not n equals 0 any longer, but k equals 0, because k is just going to be n itself. So we'll have, this is c sub k and x sub k, or x to the k. So at this point, you can see that as we're looking at this, things are looking a little bit better. They truly are, but here's the problem. As we're really wrestling with this, you can say that our counters are off. You can look right here, and we're finally going to deal with this strange issue of k equaling negative 1. And we're going to have to plug that in and see what we get. So I'm going to have, here's our x to the r. Now, if I let k equal negative 1, down here, we could see very quickly that we would get a c sub 0. So we'd get a 3, and we'd have a c sub 0. But, as k is equal to negative 1, the 1 and the negative 1 cancel. We'd have an r. And then we'd have an r minus 1 right here. And this x sub 0, or this would be an x to the negative 1 right here too, wouldn't it? And our video is about to end.